Okay, so I quickly just would like to introduce now this tutorial 2, where now the task finally is to load the data and look at the data. And I would just, like to give you a few tips and tricks what to take care about now. And I mean, this slide here we already managed to talk about in the first lecture this morning. And really, the aim of this tutorial 2 is just that you, again, yourself practice applying these 6 criteria, okay? That's the whole idea of it. So we can go through all of that. What's very important about this data set is that you will first do it label-free. So you will, when you follow the tutorial, first remove all the heavy transitions again. Go through the analysis once label-free. And then you can load the heavy transitions again back and look at it heavy and light. And the idea is that you see a bit the difference and how valuable these heavy transitions can be. Okay, so don't be surprised. In the moment when you have light and heavy peptides available, you can always check that they look like this, right? The light and the heavy peptide should really mirror each other in terms of their relative intensities. And they should also be co-eluting and having the same peak shape. In the moment when this is not the case, when you see a significant retention time shift between what you think is the light and the heavy, then it's not the same peptide, okay? We are working with 13C, 15N labeled peptides. They must co-elute perfectly in retention time. Yeah, and then just to bring you to this point, because I think it's also very important, is that the different dot products that we have in Skyline. So I already introduced you the dot product that makes the correlation between the SRM traces that you see and your library spectrum. That's what we call the dot P, and you will always see it here behind your precursor. You see the dot P for the light, and here is the dot P of the heavy. And good dot P's are always in the range, I would say, above 0.8. But there is not cutoff that people use. It will also depend on where this spectrum here comes from, whether it was acquired on the same instrument type or on another instrument. So there are many reasons why it can be good or bad, or so it's not so black and white to see it. But ideally, you would like to have dot P values in the range of 1. 1 means perfect fit. 0.9, 0.8 is all okayish. But then there is a second dot P within Skyline, and that's what we call the R dot P. Why is it not showing? It's probably here you see it. And the R dot P value, this is calculated in the moment when you have a heavy and a light peptide in your sample. And it's the correlation between the intensities of heavy and light. And you see it here, R dot P, that's the R dot P. It's only shown for the light, not for the heavy. It's the same, of course, for heavy and light. And the R dot P value, this should always be very, very good, because that's a definition of how it is. If the R dot P value is 0.8, there's definitely something wrong or some interferences going on, and you should check that. R dot P values is on the same instrument, measure the light and the heavy peptide. It should always be very close to 1. Okay? So R dot P and dot P values you should look into. The R dot P you will only be able to see once you have heavy reference peptides in there. So in the label-free analysis, it will not be there. Okay? So the way, and this is also described in the tutorial, the way how you should approach this, as soon as you load your raw files, the 9 SRM files into Skyline, you go through the Skyline document in a way 3 times. The first time you should go through it and being focused on identification. Has Skyline picked for me the right peak? Okay? So you visualize everything with having in the back of your mind, are you convinced that this is the correct peak? So you apply the 6 criteria and you say, okay, Skyline has picked the right peak, or no, here's something wrong, I need to change the peak that is selected. Once you're convinced, now we have only correct peaks in there, and it can also be that you need to remove a peak completely because it's just not detected. Then you look again to the data from the view of ideal quantification. So you no longer check whether this is the right peak or not, but now the question is, are all transitions of good quality? Are they reproducible over all the 9 runs that you have? And do I maybe need to remove certain transitions to get a better quantitative result? Okay? And you should also make sure are the peak boundaries good. So sometimes Skyline will make a very broad window for some reason. So you should, in this quantification screen, check that everything is optimal for quantification. And it really helps to separate these 2 points sometimes and go through the document twice. And the last time you just check once more everything until you're really sure that this is now a very good document for quantification, and only then you would start exporting the data and work with the quantitative data afterwards. Okay, I think this, and here are just a few more examples, just that you get a better feeling of interferences. So here, for example, is a peptide where the yellow transition is interfered. You can see that this yellow transition compared to all the others has a much higher background. Very often, actually, this is the case that this transition is very close to the precursor value. So when you have transition that has a mass close to the precursor value, it's just much more noisy. And that's also the reason why in this document that I showed you, we exclude precursor, some masses around the precursor value in Skyline can do this now automatically. Or here you see that this blue transition has this really big interference very close to the peak. And if you would set the boundaries somewhere here, you know, a big chunk of this interference would go into your quantitation. So ideally, you would just throw it out, the blue transitions. And you can throw transitions out either for the whole document simply by selecting them in your targets list and just delete this transition, and then it will be kicked out from all runs. But in theory, you can also kick out transitions per run. But usually, if you want to quantify all runs together, I would always recommend throwing transitions out for all or for none. Okay? So just select them in your target table and delete the transitions you don't like. And what's also a bit particular about the data set that you work with here is that there are proteins that are literally absent in condition 0 hours. So they're not detectable, and they come up nicely when oxygen is lacking. And that's often a very tricky case when you do shotgun proteomics to identify or to quantify absence, right? And that's one of the cool things about targeted proteomics, because we can actually also quantify the background in this sample where the peak is not there. And you can do this in label-free quantification also by using interferences that are close. For example, you see here that there is a blue and a purple interference in that range, which actually is exactly this here. So you know that in that range here, that's the area you would integrate, and we would say this is the background intensity. So the real concentration of that peptide in that sample should be below this background. It will give you the most conservative ratio when you calculate it, and you must specify this is the background value, but you can keep on working with this data set. So your task is to also quantify these samples where there is a peptide missing, and when you have synthetic peptides spiked in, this background integration is even much more easy and straightforward and even better, because you simply use the heavy channel, which is the heavy spike in peptide that is constant through all the samples. You can use this to set the boundaries and then just specify that here, this is just a background intensity value for the light, and here you start quantifying really the peptide. Okay? Yeah, I think that's it. That's all I wanted to say. Those people who are finished, just go ahead and play a bit with the data, and the others just finish this tutorial 1 and do tutorial 2 tonight in bed. Homework.